Hello, linear algebra students. Let us begin Module 12, Determinants. A determinant is a function, a real function, defined for square matrices. And depending upon the size of the square matrix, we have to employ different definitions, related but different. So let's begin with the simplest case. If we have 1 by 1 matrices, then the determinant is just the matrix itself. So determinant of, say, this matrix, 1 by 1 matrix, -5, is just itself, -5. Determinant of, say, square root of 3, for example, is square root of 3, and so on and so forth. Too trivial. Okay, let's do a little bit less trivial thing, alright? The determinants of 2 by 2 matrices, AD minus BC, and here is the practical method. Multiply the principal diagonal, A times D, and that's plus, and multiply the other diagonal, B times C, and that's minus direction, and add them together, we have AD minus BC. That's the definition of the determinants for 2 by 2 matrices. For example, here is the determinant problem. Let me just make up a problem. 2, -3, 5, 2 again? No, something like this. Okay, alright. AD minus BC, so 2 times 7 minus -3 times 5, so that's 14 plus 15, isn't it? Minus minus plus, so that's 29. So you can do this kind of computation. It's rather trivial, so I did not assign anything here. Instead, let's go over to some theory, and one of more important application of the determinant is the inverse matrix. A 2 by 2 matrix is invertible if and only if AD minus BC, its determinant, is non-zero. Moreover, we have this inverse matrix formula here, 1 over AD minus BC times this matrix, which was obtained by switching the principal diagonal and then putting negative to the others. The proof is rather simple. Just multiply these two matrices together and then simplify. You're going to get 1, 0, 0, 1. No problem there. So that's a foolproof. And whenever this expression is valid, you can do this kind of matrix computation. So this highlighted part is the inverse matrix of this, AB minus CD. Now, what if this expression is invalid? Well, nothing wrong about this. So the only thing that can go bad is this fraction. In that case, everything is moot, and the original matrix is non-invertible. Oh, by the way, this computational formula here is for 2 by 2 matrices only, but the conclusion here, the determinant being non-zero, that applies for higher order determinants as well, higher order square matrices as well for their invertibility. So please remember this. Actually, please remember everything. This conclusion, yes, and also this formula as well. Okay. I didn't write any application problem here. I mean, I could have written something like calculate the inverse matrix like this. I could have. And it would have been an easy problem if I did that. This 1 times 6 minus -2 times 4, just determinant computation, and then switch the principal diagonals, and then put negatives here, and oops, and that would have been the complete proof. I mean, complete solution, excuse me. And maybe you're gonna do just a little bit more computation. Let's see, this is 6 minus plus 8, isn't it? So this whole thing is going to be 1 over 14. Okay, but that final simplification is not really necessary. Okay, so much for determinants for 2 by 2 matrices and inverse matrix formula for 2 by 2. Let's go back to theory. The basic properties of determinants, the fundamental properties of determinants. We can express the determinant of 2 by 2 matrix, which is like this, in this kind of double variable function form. First variable is the first column vector, blue column vector, and second variable is the second column vector, red column vector. Then you can regard determinant as a double variable, vector variable functions, where each vector variable is a two-dimensional column vector. Then this determinants function satisfies these three conditions, d1, d2, d3. Bilinear, which means two linearities put together. Bi means two, right? Alternating, and then finally identity property, the simplest of them all. Determinant of the identity matrix is always 1. You see, determinant of identity matrix 1, 0, 0, 1, calculated. Let's go to the other two. Bilinear, what do you mean by that? Bi means two, so it's two linearities put together. Here, the second variable stay the same, and the first variable we have a linear combination of ax plus by, and as you can see, it is separated the way you see in the right-hand side. That's the linearity with respect to the first variable. Also, we have the linearity with respect to the second variable. First variable a1 stay the same, and in the second variable we have the linear combination of ax plus by. And as you can see in the right-hand side, you have a nice separation. So we have two linearities put together, called bilinearity. And we discuss this bilinearity when we are dealing with those scalar products. Similar concept, not exactly the same, but similar concept here. As far as bilinearity is concerned, it's the same. Now, this is different. For scalar product, we have symmetry. So if we switch the two columns, then we have the same thing. But here, if we switch, we have negative. That thing is called alternating. Now, how do you prove this alternating property? The proof is really simple. Here's the proof. A, B, C, D. So AC is my first vector. BD is my second vector. And we have AD minus BC. And let's do a little bit of manipulation. Negative of BC minus AD, and that happens to be the same as the determinant of this matrix here. BC, which is principal diagonal, and then AD, that's the other diagonal. So determinant here is BC minus AD, and this negative, consequently, we get this. The proof of alternating is really simple. Just put those into the definition and then work those out. Okay, the proof may be just trivially simple, but there's another thing that you have to remember. So if you switch two columns, just put negative sign. That's alternating property. And this property follows immediately because if you have two identical columns, then even if I switch, I'm going to get the same thing because x and y, they're the same. We have x comma x. So what is the real number that stays the same after taking the negative? It can be only 0. So alternating property gives you this 0 property. I don't know what should be the name. If you have two identical columns, then the value is 0. This property is an immediate consequence of an alternating property. And This one is very, very useful as well. So please remember both of them. So, okay, what did he do? Determinant of identity matrix is 1. Okay, that was easy, just brute force computation. And then alternating property, and then its immediate consequence. The proof was easy. Okay, let's do something that's not that easy, still not difficult, but needs some work. Okay, let's prove the bilinearity. And I'm going to prove only the first one. Second one will be pretty much the same, and, well, I take it back. It's not even pretty much the same. Exactly the same, except for the position. So I'm going to leave that to you. I'll do only the first one. So, okay, here we go. Here's the proof. And let's begin with ax plus by. So a, this is x, two-dimensional column vector, and b, y, this is y. So we have ax plus by in two-dimensional column vector form. And the second column vector here, well, I'll simply leave them as it is, as is. A12, A22, as we had B here. And then let's put these two together. And that's what we get here. AX1 plus BY1, AX2 plus BY2. And then we have one column vector, another column vector. So we can put everything together as one 2x2 matrix. So 1 1 term, 1 2 term, 2 1 term, and 2 2 term. Okay, ready? Let's put it into the definition of this determinant for 2x2 matrix, crisscross, AD minus BC form. So multiply principal diagonal, that's the first term, and multiply the other diagonal and subtract, that's the second term. Okay, here let's do a bit of an algebraic manipulation. Here's A, and then there's another A, so we're going to put these two together. A, x1 times A22, alright, and here's another A, x2 times A12, but that's negative, so we get that. And that expression is the crisscross coming from this determinant. Let's go back here. I want these two a's as a single factor, so take a out, alright. So x1 times a22 minus x2 times a12, that gives me this, and that is the same as this determinant. Likewise, we can do the same thing to this b. Take this b out, and there's another b. So, okay, how about this b? y1 times a22, y1 times a22, and how about this b? y2 times a12, but that's minus. So minus a12 times y22. So we have this AD minus BC form, crisscross form, and that happens to be this determinant. So that completes the proof. Or you can start from here and then just follow this simplification, and then get this, stop. And then we can start from here and then go to definition, crisscross, and then get that, and then check if these two expressions are identical. You can do those. That's rather brute force real variable computation, so just a routine algebra, that's not going to be too much of a problem. If you don't like the way it was handled, from left hand side, just calculate to the right hand side. That looks elegant, but then again, from here to there and then over there, it's kind of going back upstream, so it may not feel very straightforward to you. In that case, just start from the left-hand side and simplify, get up to here. And then start from the right-hand side and simplify, get up to there. And let's see if these two are the same. And checking these two are the same, that's not going to be difficult at all. Tedious maybe, but nothing difficult here. So what's the conclusion? We proved these three basic fundamental properties of determinants for 2x2 matrices: bilinear, alternating, and identity properties. Okay, going well. Here are some further properties of determinants, and they're all going to be, okay, did I say they're all going to be? Okay, first and third are going to be simple. The second is going to be not that simple. Not difficult, but it's going to be tedious. Okay, let's do first one. Determinant of A transpose is itself. And that's easy. All you have to do is to use this direct definition. So this is the determinant of the transpose matrix, right? AD stay the same, and then we switched the others. B and C we switched. And calculate the determinant, and we get same AD minus BC. So this is actually determinant of A transpose. And this one is determinant of A. So you see, determinant of A transpose is the same as determinant of A. Okay, this one looks a little bit better, so this problem is too trivial for an exercise, but yet I provided full proofs, so oh well, I'll simply write as proof. And then, okay, all right. Okay. Next, determinant of inverse matrix. This problem is left to the students. Okay, there must be a reason why I left it. How about this one? Determinant of products is the product of the determinants. And the proof is, what can I say? It's kind of like this. So if you start from the left-hand side and get something and then backtrace the algebra and then go into the right-hand side, it may be possible, but I tried, but it was a little bit difficult to follow, to tell the truth. So I started from the left-hand side and got somewhere. I started from the right-hand side and got somewhere. And then I used my brute force algebra to check this one and then that one are actually the same. And let's follow. Determinant of A, B, C, D, that's AD minus BC. Determinant of U, V, X, Y, it's UI minus VX. And that's just a definition. And after that, it's just brute force foiling expression. Next, matrix ABCD times matrix UVXY. That matrix computation turns out to be this, and what can I say? It's just a brute force computation, nothing more than that. First row, first column, so AU plus BX, that's my 1-1 term, and then repeat this, and get all these entries. And then we just calculate the determinant using the usual crisscross. AD, this times that comes over here, minus BC, this times that over there. Okay, there are already A, B, C, and D here, but I don't think that caused too much trouble. AD minus BC over there, I meant by this crisscross. And then checking whether this and that are the same or not, it's just tedious routine algebra. Turns out the same.